Now let us look at the next component we are going to look at are what are called as brake chambers. So let us look at what is called as a brake chambers. If you look at the foundation brakes, okay, in most of the heavy vehicles, once again they are going to use drum or disc brakes, but for the time being let us look at a drum brake and then we will see what happens. Okay. So, yeah, of course, sorry, there is a typo here, this should be diaphragm, all right, yeah, sorry about that. So, what happens is a brake chamber is that this compressed air, right. So, let us say we consider one of the brake chambers, front or rear, the compressed air comes through all these walls, it enters the brake chamber, right. The brake chamber is a diaphragm which is essentially supported by a return spring. Now when the compressed air enters, what happens? The air pressure is going to act on this side of the diaphragm, it is going to displace this diaphragm, and the diaphragm is attached to a component called as the push rod. The push rod is nothing but a rod which is pushed out of the brake chamber when the compressed air enters the brake chamber and generates a mechanical force, right. So, when the push rod comes out of the brake chamber, it essentially rotates a component which is called as a slack adjuster. So, a slack adjuster is nothing but a lever, okay. So, on which a force is applied by the push rod. So, the lever is mounted on a shaft on splines, we have already seen what splines are, right. So, teeth like projections. So, when this lever is pushed or the slack adjuster is pushed from the top, what is going to happen? It is going to rotate about this axis or the shaft axis on which it is mounted. So, the slack adjuster will rotate. When the slack adjuster rotates, the shaft will rotate. Then on the other end of the shaft, we have a cam in the shape of an S which is mounted. So, that is why these brakes are what are called as S-cam brakes. Okay. So, if someone talks about S-cam brake, they are in essence talking about this heavy vehicle brakes where the foundation brake is a drum brake with an S-cam. Okay. So, this is nothing but a drum brake with a cam shaped in the form of a S, that is an S-cam brake. So, what is going to happen? The push rod will rotate the slack adjuster, this S-cam will be rotated because it is mounted on the same shaft. Now then what will happen? These rollers will rotate on the, will move on the cam profile. When the S-cam rotates, the cam has a profile, right. These rollers will move on the cam profile and they will push the brake pads out. So, what is going to happen? The brake pads will move, brake shoes will move out and contact the brake drum. The drum brake operation is the same, okay. Once you have an actuation force on the free ends of the brake shoes, you know, they are going to rotate about the pivot and go and contact the brake drum and generate the braking torque. Now the question arises, why such an elaborate mechanism, right? Because in a hydraulic brake system we essentially had a wheel cylinder that applied the actuation force. The wheel cylinder was fitted in this drum brake unit and fluid pressure came in, hydraulic pressure, brake fluid pressure came in and actuated the drum brake. Here why do we have such an elaborate mechanism? There are multiple reasons to that, right. The first reason is that when you look at a heavy vehicle compared to a passenger car, its mass is more, right. Then if you want to brake a heavy vehicle at the same deceleration, the braking force should be larger. I am sure all of us can agree to that, because m times a would be higher for the same a, right, for a heavy vehicle as opposed to a passenger car. So we need to essentially generate a larger braking force. that translates to a larger braking torque or more output from the drum brake, right, in a heavy vehicle. So, yes, the dimensions of a drum brake are going in a heavy vehicle, in a heavy vehicle air brake system are going to be slightly larger than that in a passenger car, but it is not going to be as heavy, sorry, or as large to have a huge increase in the brake torque. So, for example, let us say we take a car that weighs 1000 kilograms, we take a truck or a bus which weighs 10,000 kilograms. I am just taking round numbers so that we can argue easily, right. So, we need one order of magnitude higher braking torque. Do we have, will we essentially increase the dimensions of the drum brake to such an extent that we get an order of magnitude increase in the braking torque? Unlikely, right. So, what we may need to do, we need to increase the actuation force. The brake factor can be adjusted, but then like we need to have more actuation force to get a higher brake output, is it not? That is point number 1. Now, if I need a higher actuation force, I need a bigger actuator. So, and or a larger operating pressure, is it not? Right, actuation force in these fluid based actuation systems will be pressure times area at steady state. So, if I want one order of magnitude more actuation force, I need higher actuation pressure or higher actuator area or preferably both, right. Now, actuator area is constrained by the dimension of the drum brake. I can't put a big actuator in the space available. Actuating pressure in air brakes is one order of magnitude lower than that of hydraulic brakes. See, this is our maximum of the order of 10. There you can have brake pressures in a hydraulic brake system, the brake pressures can go up to 10, the order of 10 power 2 bars, right. So, you can see that the maximum operating pressure in an air brake itself is one order of magnitude lower than that of a hydraulic brake. In fact, we would have wanted the other way, right. So, you can see that now I have a huge deficit, right, because the actuating pressure is smaller than that of a hydraulic brake. Then how do I generate higher actuating force? So, for that we use this mechanism. So, what we do is that we use a combination of larger actuator area and lever arm action to help us. So, we put a larger actuator outside the drum brake unit in the form of this brake chamber. So, now I hope it is clear why we need a brake chamber outside the drum brake unit, right. That is reasonably large. So, that is going to generate some force, and then we have this slack adjuster that is going to provide a magnification, and then like the torque on the slack adjuster shaft is going to be converted to an actuation force by this S-cam radius, right. So, important parameters are in the order, I will just write. So, brake chamber area, these are all important design parameters that allow us to regulate what is the magnification obtained, right. Brake chamber area is one, the slack adjuster arm length is another, because that helps us in figuring out what is the torque that we get for a, what to say, given push rod force output, right. And the S-cam radius, because the S-cam radius dictates what will be the force on the brake shoe, the actuation force for a given torque, right. Torque divided by the S-cam radius will give me the actuation force. So, these are important design parameters that help us in meeting the actuation force requirements for a heavy vehicle drum brake to match the expected increased brake force output as opposed to a hydraulic brake. Is it clear why we have this mechanism? But we also use disc brakes. Okay, today in heavy vehicles disc brakes are also becoming popular. Once again the actuation medium is compressed air, but the mechanisms will be slightly different to account for the fact that we are using a air disc brake. Okay, so that is the main difference, but the concept of the disc brake remains the same, right. Okay. So, this is the S-cam brake. So, if you look at a picture or a photograph of that, just to give a perspective, So, this is how it look like. So, essentially we can observe that the air enters into the brake chamber. Okay. So, this is the push rod. So, we can see the slack adjuster that is going to be rotated, and that is going to rotate the S cam. Okay. So, this is the S cam, and when the S cam is rotated, the rollers are going to be displaced on the profile of the S cam, and the brake shoes are going to be pushed outside, right. They will go contact the brake drum and generate the decelerating force, alright. Okay. So, now this is what is called as a service brake chamber. Okay. So, what happens in normal operation. Okay. Shortly we are going to look at what happens under emergencies, like, and what happens when we have when we want to park a heavy vehicle. Okay. So, we are going to come to that. So, if you look at the slack adjuster per se, this is just a simple schematic to show what are the components in a slack adjuster. So, as we that is an important component because it is going to convert the force applied by the push rod into a torque, right. So, we can observe that the slack in the slack adjuster body we have this worm gear, like, which essentially has the splines on the inner side. So, the splines are used to fit the slack adjuster on a splined S cam shaft, right. So, the S cam shaft, this is the S cam shaft, right. The shaft has one end as the S cam, on one end is the S cam, on the other end the slack adjuster is connected on splines. So, then there is a worm gear with an adjustment mechanism, and the slack adjuster has a hole where we can mount the push rod, right. So, the push rod is mounted at this point. Okay. So, if you look at the slack adjuster arm length, it is the distance between the center of this mounting hole and the center of the spline shaft. Okay. So, that is the slack adjuster arm length. Now, why do we require this worm shaft, and why do we require adjustment? Because as we discussed with operation, the drum brakes will wear out. Now, what happens is that if you go back to the schematic, if the gap between the brake drum and the brake lining keeps on increasing, what is going to happen is that the stroke which is required for the push rod to enable the brake lining to contact the brake drum will increase. I am sure all of us can appreciate it, right. As the brake lining wears out, the stroke of the push rod required to displace the brake shoe and press the brake lining against the drum would increase. But however, please note that there is a constraint on the stroke of the push rod, right, that depends on the dimension of the brake chamber. So, the stroke of the push rod cannot keep on increasing forever, right, without a limit. So, at some point or at some limit, the push rod stroke will reach a state wherein this diaphragm may start hitting the brake component of the brake chamber components, and the force output from the push rod is going to go down or decrease. Okay. So, if we plot the brake chamber force output, this is push rod stroke, what is going to happen is the following. We are going to see a drawing diagram something like this for most operating pressures. Okay. So, some characteristic curve like this. So, typically if you install a new brake lining, we are going to have some baseline stroke, let us say around half an inch, right. That is a typical stroke such that the drum brake is properly applied. Now what happens is that, like, as the stroke keeps on increasing, right, as the brake linings get worn out or the brake drum expands due to thermal expansion and so on. So if the push rod stroke reaches what is called as a readjustment limit, right, then we can see that the output from the brake chamber starts falling down, right, because the diaphragm is going to go and hit the other surface of the brake chamber. So that is going to take up some of the force output, right, from the brake chamber, right. So the push stroke of the push rod is an important parameter that provides us with information about the health of the air brake system. So it is a very useful diagnostic and prognostic parameter which tells us what is the state of this air brake system, right. So that is a very important point, okay. So let me write that. So please note that the output force from the brake chamber reduces significantly once the push rod stroke exceeds the so called readjustment limit. So once the readjustment limit is exceeded, the brake force output reduces rapidly, right. So and that is something which you and I do not want. So the readjustment limit is specified by the manufacturer, okay. So that is why the slack adjuster has an adjustment mechanism in the form of this mechanism. So what happens is that there is what is called as an adjustment nut, and someone has to go underneath the vehicle and check out this stroke of the push rod. If it's very high, what the mechanic does is that, like, they rotate this adjustment nut so that the initial position of the worm gear itself is rotated, right. So that the even with the brake being released, the initial position of the brake pads are closer to the drum. Of course, this has to be done carefully, right. We do not want the brake linings to be excessively worn out. Then even if you use this adjustment mechanism, we will not get proper brake force output, right. So it has to be used judiciously, this mechanism for adjusting the initial position. So there is an adjustment nut which can be turned to rotate this worm gear such that the initial position of the brake shoe relative to the drum itself is brought closer, right. So that is the purpose of the adjustment mechanism. So based on the adjustment mechanism which is there, if someone has to do it manually, we have what is called as a manual slack adjuster, right. And if the adjustment happens automatically when the vehicle is in operation, there is something called as an automatic slack adjuster, okay. So these are two mechanisms that are available, okay, for enabling this adjustment operation, right, okay. There is another point, like, which is important as far as air brake systems are concerned. In the presence of a leak in an air brake system, the sensory feedback available to the driver is lower than in a hydraulic brake system. As we discussed in a hydraulic brake system, if there is a leak in the fluid circuit, what is going to happen? We will see that our pedal is going to become softer, right, to apply what is called as a pedal sinkage effect, right. So that is going to be a result of the fact that we are losing brake fluid there, right, and we are losing that fluid pressure. So the reaction that comes to the driver is reduced. What was the physics behind it? The physics behind it was due to the mechanics by which the hydraulic brake system functions. there the brake fluid is pressurized by the human force. Of course, the human force is magnified by mechanical and other means through a vacuum booster, but ultimately the human effort, though magnified, is finally used to pressurize the brake fluid. So, if the pressure drops, that is going to directly influence the human or the reaction force provided to the driver. In an air brake system, the human effort does not pressurize the operating medium. So, consequently what happens is that the tactile feedback or the sensory feedback available to the driver in the presence of a leak in an air brake system is smaller, and that makes it a challenge for human beings to detect leaks. Okay, so that is another challenge with air brake systems. Okay, so the tactile feedback available to the driver is lower in an air brake system in the presence of a leak. So, obviously we can observe that a leak in an air brake system not only reduces the force output from the brake chamber. Why? If there is a leak, the pressure will drop, right? Particularly under emergency braking conditions, the maximum pressure available will drop in the brake chamber. If the maximum pressure drops, then the maximum force output also will be lower in the brake chamber. Now, another point is that, like, if there is a leak, what is going to happen? The brake system is going to try to pump in more air into the brake chamber. Consequently, in the treadle valve and relay valve, the connection between the supply and the delivery will always be open, even if we have medium brake applications, because why? There is air leakage, right? So, that is going to bleed more air from the reservoirs. So, we are going to waste energy, right, is not it? Because we are using more air from the reservoirs to maintain a certain pressure. So, those are two detrimental effects of leaks. The operating force or the output force reduces, and also we end up using more compressed air source, right. So, that is something which we do not want to do in a air brake system, right. So, the last component which I am going to discuss are parking brakes. So, let us look at what happens in a hydraulic brake system. So, I am calling as a mechanical parking brake first. So, as we mentioned when we discussed this configuration of disc brakes in the front and drum brakes in the rear, right. So, I also told that in addition to the reasons that we discussed, there is also one more reason why drum brakes are still popular in the rear, and that is due to the easier integration of parking brakes in the rear. So, if you take a typical passenger car, how do we engage the parking brake? We pull the hand lever, right, which is available next to the driver. So, the parking brake is mechanical in nature in most passenger car brake systems, right. So, what happens is that when I pull the lever, this cable, you can see the parking brake cable is going to be pulled. So, when the parking brake cable is being pulled, you see that this element to which the parking brake is connected, this lever arm is pivoted about here, and that is going to generate a magnified force on this parking brake strut, is it not? Because this end is going to move like this, right, once I pull the cable. So, this lever arm is pivoted about this pivot. So, consequently at this point the force will be magnified. So, the magnified force will be applied on this parking brake strut. the parking brake strut lies on this brake shoe. So, what is going to happen? It is going to push the brake shoe against the drum, and because of the self adjustment mechanism it will also rotate this and press this brake shoe against this drum, right. It will try to push it, but anyway parking brake is only a relatively smaller output brake, right. We just want to ensure that the vehicle does not move when there is a disturbance on it, or when the vehicle is parked on a slope, W sin theta does not make it move down the slope, right. So, we just provide enough brake torque, right, to enable that it is stationary. That is the function of a parking brake. So, obviously we cannot expect a parking brake to replace a service brake. So, I hope now the subtle difference between parking brake and service brake is clear, right. Service brake is used for a normal brake application, parking brake has a specific functionality, right. But you can immediately observe that the parking brake also uses the same components as that of the service brake. Yes, there are some more components, these what to say, the basically the arm which is used by the parking lever which is used by the driver, the cable and the lever arm and the strut, those are additional components which are there. But then please note that one uses the same drum brake to enable this parking brake functionality. The parking brake can also be used as an emergency brake. In the case that the service brake fails, let us say you have fluid pressure loss in a hydraulic brake system, we can still enable the parking brake to generate some brake output, right. So, this also acts as an emergency or secondary brake. Of course, it cannot replace the service brake, please remember that, right. Okay. So, we can observe immediately that this is one important advantage of using a drum brake in the rear, because the parking brake is easily integrated with a drum brake on the rear using simple mechanical components, right. Now, what happens with a disc brake? So, that I leave it to you as an exercise. How is this achieved? In let us say a car with disc brakes on all 4 wheels. Okay. So, please find out, right. So, we will discuss about parking brakes and heavy vehicles in the next class, and then we will move further. Thank you.